Welcome everybody to this talk. It's called Doors of Durin, the Weltgate to Siemens S7 Silicon. There's going to be about some research that we performed on S7 PLCs, which are programmable logic controllers from Siemens. And we specifically performed some research on the bootloader code as well as the firmware itself. And we will show some of the special access features that we found in there. All right, we are 3 people who worked on this. It's Ali Abbasi, who was a PhD student at the time, and I helped him then. And since then, I got a PhD student myself, and he a postdoc researcher. Sadly, he couldn't get a visa in time. He asked for a minute of silence about this, but sadly, we don't have time for this. So let's start with the presentation. So as an outline of our talk, first we want to get into a bit of what is automation, what do we need it for, and how is it used in the industrial context. Then we want to get into the hardware of a Siemens PLC, what does it look like on the inside, what components are on the boards and stuff like this. Afterwards we see the software part of it. First the startup process, then some components of the Siemens firmware to give you an overview of what it can actually do, and also some details on where you might want to find different pieces of functionality inside the firmware itself. And afterwards we will talk about a special access feature which we found inside the bootloader itself and have some demos about it as well. All right, so if we think about process automation, the first maybe pretty trivial example is what we would do at home. We have some temperature sensor, and we would like to control the heat inside our house, for example. And in this simple application, we would have the sensor on the one side telling the heater to either increase or lower its heating power based on what kind of temperature we would like to have. So this may get much more complex, right? So if you look at a factory where you do actual products that you want to produce, or you want to maybe steer some chemical processes and stuff like this, you get into much more complex processes, which we can monitor via something that we call HMIs, which are human-machine interfaces. You can see some of those here and some operators sitting in front of those. There is a wealth of data which can be potentially displayed to those operators, and a lot of detail that they have to take care of. But in order to get this data, we have to have actual sensor information that comes to those places, and this is not as trivial as as you can probably imagine. And what we use for this is PLCs. One of the like a diagram of how this typically works is here. You can see here it's the inputs, which are typically sensor values. This could be like a temperature. This could be the level of a liquid inside a tank, something like this. And then there are outputs. The outputs which steer actual motors, actuators, and something like a pump, for example. And in the middle, we need some logic, and we encode this logic in programs, which in the PLC field are ladder logic programs or structured text programs, and those are downloaded onto the PLC, which then calculates the logic based on the inputs that it gets and puts out the outputs in order to steer such a process. This can even get much more complex than this. For example, if you had a lot of different PLCs from different times when you bought them, they speak different protocols, and it kind of gets a zoo of PLCs basically. And inside a factory, you could start putting in an additional appliance which takes care of translating those protocols and making those PLCs work together. But we will not focus on those kinds of control servers at the moment, but on PLCs. Here we can see some applications of PLCs in, for example, a chemical plant or in the electric grid or manufacturing, all pretty critical parts of our infrastructure which we don't want to have damaged at all. For example, if you went to Google some images about chemical plants having some accidents, you can just basically see a melted plant just down there. This might be by accident, but also we want to prevent this happening on a malicious intent. Here we can see some recent attacks as well. It started in '99, where first reconnaissance activities were reported, and then in 2010 we had kind of the big bang, you could say, of intrusions into those systems with Stuxnet, which you probably all heard of. If you look into the details and kind of brainstorm what goes into getting this operation to tick, it's pretty impressive, and a lot of people with a lot of different backgrounds have to work together to make it work. And in 2015 to 2016, we could observe some of those attacks on the Ukraine power grid just before Christmas in those 2 years, shutting down parts of the whole electric grid of a city or so. Here we can get some feeling about where Siemens is positioned inside the market. So together with Rockwell Automation, we can see that it's more than a 50% market share. So if there are any issues in one of those Siemens PLCs, you can imagine them to be spread around a lot of facilities, and that's where there can be quite a bit of an impact if there is any security vulnerabilities there. Okay, here we can see the specific PLC that we are going to target here, which is the S7 1200. If you exclude the logo, which is a bit of a even smaller sample, it's one of the more accessible PLCs. It's around 250 euros, I think, which is rather accessible in comparison to other bigger appliances. But then if you start like frying a PLC or two, maybe dropping one, then it can still get quite expensive, I can tell you. The applications get, as we already saw before, are in pretty critical environments. Here we can see the actual hardware view of such an S7 1200 PLC. On the top, you can see the first layer of PCB boards. It's different PCBs stacked, but all the magic that we care about is going on in the first layer, which we can see some details about here. The left-hand picture you can see is the top side of the first layer of PCB, and it has some of the main components there. For example, as you can see, the ARM CPU, which does the general purpose computations, and then also the flash chip, which holds the firmware image, as well as some RAM, pretty sizable in fact. On the right side, we can see the flip side of the same PCB, and there we can see an SPI flash chip, which is smaller and takes and carries the bootloader code. First of all, what we looked at was the CPU itself. We wanted to kind of get a view of what exactly we're working with, and this is some decapping of the ARM CPU, and you can see the exact models on there, which is a Renesas model from 2010 in this case, and we also looked into the exact hardware ID that this Cortex R4 chip, as we can see here, is made of. So there are instructions in the ARM instruction set that you can query those different values, and you can pass those bit fields, and then you can see that it's in fact a Cortex R4 core with a specific revision number and so on. So if you're assuming that you're working with a specific device, you may as well check, and this is a way you can check that you're actually on the exact version that you think about. Here is a look at not the computation side, but the storage side. We can see the different flashes in a close-up view for the firmware one, the bootloader one, and the RAM chip as well. It notably carries an MPU as well, so there is some possibility to configure memory protections. So in order to care about any memory corruptions that could occur, or maybe also the running code inside a data section. So you can try to prevent this by using the MPU, which is also used, as we can see in later slides. Oh, I think I skipped one there. Did I? Yeah. This is a more detailed look on the bootloader chip. Here we can see the different chips, the same chip in different views, and what we can see on the right-hand corner, we can see a little mount that Ali built. This is a little bit of an exclaimer from my side that he did most of the hardware part, and I'm more of the software guy. So he created a mount on top of the actual Cortex R4 CPU, which roots connections down to the bottom side of the PCB and connects to the bootloader chip. So we had a mount to get better access to the bootloader chip, so we could play around with it more easily. We also took some X-ray of the PCB itself. We are using this for an ongoing project, but it's also was used in order for us to be able to find specific functionality of the PCB and maybe some connectors, which we will see in 2 slides. Here first we have the PCB itself. It's 2-layered in its core, like the top and the bottom part, and then in the middle we have a plate being connected to ground, and then VCC as well in the middle. Here's one of the functionalities that we actually were after, which is core site. I don't know if anybody has heard of that, but it's kind of equivalent to Intel PT process trace, which allows you to, after the fact of execution, see some trace information about code coverage and the like, which could be interesting in both reverse engineering applications, maybe understanding an application, or also maybe fuzzing as well. Now we get to the software side of things, which I was much more involved with, as a matter of fact. Here you can see a bit of sizing information. So it's like 13 MB of just flat binary code, which is kind of a bit. You can see here, I'm not sure if you can see that. It's about 84,000 functions. So it's a nice mating call from a firmware image. If it's that much for a reverse engineer, you can obviously not look at everything. Also, we can see some of the names that I provided, like some get some max size, so I'm not quite sure about everything, as you can see. But for other functions, we have quite a bit of information already, knowing what they are doing in the context of the operating system, which I will describe a bit more in detail. Yeah. So I think I applied around 50 IDA Python scripts, I guess, to get to the point of 84,000 functions. So it's you can do some automation to make your life a bit more easy there. All right. First of all, let's look at what the bootloader does in its startup process. It's kind of what you would expect it to do. The bootloader basically wants to get the hardware ready for the second stage payload to be executed. And here we see that, for example, the vector interrupt controller is set up different hardware parts, but also it checks the integrity of the bootloader code itself and also the firmware. A thing to note here is that it's using CRC32, which is only something that can check for non-intentional changes to the firmware. So if like physical memory was corrupted by some way, but if somebody got control over this, it's not a cryptographically secure checksum. So the bootloader doesn't perform any cryptographically secure checks just before running the firmware image, which is interesting to note. Also, the chip that we saw, the SPI flash chip, which holds the bootloader, was changed in 2018. It wasn't really documented by Siemens, I think, but we noticed it that there were write protections all of a sudden on this chip. Here we can see similar information, but in a bit of a different representation. But what we can also see is here in the bottom left. It's a pretty juicy thing, which is a special access feature, which we were able to identify, which we will talk about just a little bit later. So a bit of a cliffhanger here. Let's first get into the firmware and the different components of it. Here we can see an overview of those firmware components. It's kind of split into 2 parts. First of all, it's called the ADONIS RTOS internally. This is also not a documented feature, but it's just the Siemens internal name for it, as we found out. And you can see 2 different areas of services. The first one would be more general services, which you would expect from any operating system when it works in a rather complex environment. It needs to talk to its outside world, so it needs TCP/IP to work. It needs a C++ library just to do basic programming functionality, and also it wants to handle a file system. So all those components you will find on the left-hand side. There's also diagnosis and a web server, all those things which are not directly related to automation, but more to a general purpose operating system. On the right side, on the other hand, you can see that there is quite a lot of functionality which is related to automation processes, as we might expect. So for example, the MC7P parser, as well as runtime and compiler, is the runtime for the code that we can download onto the PLC, the ladder logic that we were talking about before. And also some other programming languages like the automated web programming, which also runs on the PLC. All right, now we got some information about the different memory maps and address ranges and stuff like this, which we will find in such a firmware image and while it's running. So one thing that is important to know here is that for a Cortex R4 processor, which we are working with here in this case, they bank, as they call it, different registers for every execution mode, and then you have different stacks for those modes, and it might be interesting to know in this context, if you wanted to do something like forensic work or even do some reverse engineering, it's interesting to know those addresses which we extracted here for you. We have a dump of the different memory regions as well, so if we wanted to get a little bit of an overview of where things reside in memory, we could find it here. For example, the uninitialized section, which is somewhere down here, is dealing with dynamically allocated memory. If we wanted to find some code, we would look in the text section. If we wanted to find read-only code, we would look into the RO data section. And if we wanted to look at what is going on in the boot process of the firmware itself, we would look at the TH initial section, which we will talk about a bit in the next slides. Another thing that has not been documented before is also interesting in the sense that we can talk to hardware directly, which is MMIO, memory mapped I/O, and we have some of those ranges here. We can see that different pieces of functionality and hardware is supported. For example, SPI flash is supported, of course, so we can talk to SPI directly. Or we have a bunch of timers, and we have an analog to digital controller and so on. So if we wanted to create, for example, a driver for this, we could use those ranges to implement it. Here we see, as a final thing, about addresses. We see some MPU configurations, so memory protection unit configurations. As you can see, there are some protections that Siemens put into place here. For example, the XN bit, which is the execute never, which is kind of a no, of course, as the name says, no execute bit. It's set for some sections, and we also have some protections such as read only for other sections as well. So Siemens is dealing with some of the memory protections in this case, as you can see. Here we can see the different steps that the firmware itself does as a second stage after the bootloader is executing. It kind of replicates what the bootloader does, basically sets up the hardware space and so on. So it's basically doesn't want to depend too much on the internals of the bootloader, I would imagine. But then if we go into the second stage, which is the ADONIS kernel itself, it does initialization in a kind of interesting manner, where it queries a whole table of function pointers and calls them one after the other. This is interesting to note because as a reverse engineer, we might be interested in what kind of hardware components are initialized in the system, and we can see for every hardware component, can figure out what kind of data structures are set up and how they are used and initialized and so on. So if we wanted to understand more about the internals of a specific component inside the system, we could look at some of those pointers here. For example, what is set up is a tracing system, different XML parsers, the mini web, web server, and so on. Here we can see also the file system, that it supports a file system, as we said, and some of an interesting fact that we found out about this is if you actually do some open source intelligence, you can find from actual job portals where people, previous employees from Siemens would say what they were working on before, and they would use some of the internal names that they worked on, which are not public though. So here in the one case, you could see that they are talking about ADONIS OS, and on the other hand, they are talking about a proprietary file system format, which is FAT32 compliant, and it's the power down consistency file system, which is seems to be there to make sure in case the Siemens PLC loses power, all of a sudden the file system will still stay intact. So this is kind of an interesting source of open source intelligence. Sometimes if you look for internal names or so on, we could get some hints on this in an open space as well. Here, what also has to be supported, of course, is some talking to the outside world of the PLC. As it turns out, Siemens doesn't do this by themselves. They use a third-party TCP/IP stack, which is Interniche in this case, and via some Google magic, you can find those sources as well. And here we can see that we found some prototypes and also ways of setting up a TCP connection and using it. Now something on the firmware update process of the S7 PLC as well. So there is an SD card which you can get, which is one of the ways. So it's 24 MB, $250, which is a good price to what you get percentage, I guess. So a bit of an opportunity for Siemens to earn money. We are not quite sure whether they have specific features, but it seems to be basically FAT32 parsing and nothing too special what we have seen there. The other way you could update the firmware by the firmware running firmware itself is via the web server, where you can upload a chunk of your firmware update, and it will there check different firmware signatures, or one firmware signature over a hash, which is a secure update mechanism, where I think no real issues were found with. So the firmware side of things performs an integrity check and also makes sure that this update comes from Siemens. If we are aware that Siemens indeed is the only one who holds the private key, which we, of course, assume here. We also did some reverse engineering on the decompressed firmware update file structure, so you would find those different headers and checksums and also signatures as well. You can also find the public key, which is used inside the firmware, and we extracted the address where this one resides as well, and also gave you some hints on where you could find, if you wanted to look into it yourself, the firmware update mechanism itself. All right, another component that we have is the web server, which is mini-web. It gives you some diagnostics view of the PLC. You can do some configuration on it and so on. We will see this component in a bit. It doesn't use the quite up-to-date jQuery version, for example, which would expose it maybe to some risk of XSS, but I think other than that, we didn't do too much of reverse engineering into it in the whole thing, but we saw that, for example, the password check happens at a specific address, so if you were interested in looking how this is implemented, you could find it. Here are some of the HTTP handlers that it exposes, which I find kind of funny. So they have internal APIs. So one of my favorites, I think, is lo, which is logout, or li for login, and different other ones. So I'm pretty sure if you got somebody a bit creative musically, maybe you can put those syllables together and then make a song out of it. Let me know if you found somebody creative enough to do that. I would be very happy about that. Okay, and then we see an MWSL, which is a programming language, which is a server-side programming language, which is interesting on the mini-web web server itself. So it's kind of a PHP-ish functionality with JavaScript syntax. That's what I call it. It's probably a bit hand-wavy, but it allows you to write some variables inside the system and also query some variables. And it also allows you to do some templating, injecting stuff into the HTML page. So some of it is not really output encoded, so there could be some risk of XSS there. And also I did some reverse engineering on the actual tokenization and recursive tokenization and so on of the MWSL templating language. And this also exposes some complexities, which are kind of interesting. All right, now that we looked at the firmware functionality, let's get into the meat of what we found inside the bootloader itself, as we said, which is a special access feature which we found. So it turns out if you hook up some cables just right, you get a UART connection to the device, as you can see on this picture. And I was kind of looking at the bootloader functionality, and at some point I understood kind of what it did. And then I was asking, what is all the other code about? That just feels like too much code for what I understand it to do in a normal boot up case. So what actually happens here, and then I identified this kind of functionality, that it initially on boot up, it would wait for a specific string over UART, which is MFGT1. We can just speculate on what that actually means or where it comes from, but one of my ideas as a German was that the MFG could mean mit freundlichen Grüßen, which is a German greeting. And about the T1, I don't really know. If you have any suggestions about that, I would be open to some speculation. Yeah, something like kind regards at the end. Yeah, that's true. And if the PLC actually receives this string via a UART in the first half a second of boot time, it would send you back the acknowledgement of -CPU. So if you get this back, you could know that, would be sure that this handshake has been performed and that you actually have this functionality on the bootloader itself. And then after this initial handshake has been done, the bootloader will enter a specific parsing loop of commands that you can send it. We have different commands that we identified. It's quite some commands, and the list goes on and on and on. And we didn't look into every one of those functions in detail. I kind of cursory looked at like 128 of them or so, and then gave some naming towards what I think it is. But what comes out is that you basically get access to everything that could be interesting as a low-level hardware access to do diagnostics and updates and stuff like this, to do some troubleshooting on the firmware. Examples of this could be like getting the firmware version as a first thing, or checking the bootloader integrity, but it also has a bunch of different protocols. And two of them I would like to talk to you a bit more about, which is first of all the OX80 handler. So what you do is basically after the handshake, you send it an ID of a handler that you would like to perform. So it's kind of a functionality mode, you could think about it like this. And the OX80 one provides you some features of updating, reading, writing, checking the integrity, and configuring specific devices. And different devices can be configured this way. One is IRAM, the internal random access memory of the device. And the other one is the firmware flash memory. So there you have a directly exposed API of uploading firmware to the firmware flash itself, where no integrity check is performed. Interesting about this IRAM one is that you are able to read and write from IRAM into, I think, kind of the whole section of it. It's a bit of a clunky mode, as I will get into a bit later, but this is kind of the first important handler that we have in this case, which we identified. The second one is the OX1C handler, which is also primary handler, so you can just use the handler ID OX1C after you entered this functionality. And then you would be able to flexibly call a different layer of functions. So there is a layer of functionality which resides inside the bootloader memory, and it's initially copied to IRAM, and those function pointers can then be used by this OX1C handler, and then you can say, okay, from this secondary list, I would like to use this handler and this handler. Maybe Siemens ran out of space of initial handlers or so, and this is where a lot of other of those functionalities went. So at this point, we have different handlers, and I did some reverse engineering, and then an unknown person without a UK visa asked me, how about, what can we do with it? Can we do code execution on that? And of course, I looked into it, and there was something we could do about it. So here, it's a little iteration on the OX1C handler, a little visualization here. So the normal way it would work is that this handler is called, and it looks into the IRAM table where those function pointers were copied to, and then it would just use it, and those point back to the bootloader segment, and they would perform whatever function Siemens intended them to do. But now if we combine those different handlers, which we identified before, we can actually start creating a tag out of this. First of all, we use this OX80 handler, which allows us to write to IRAM and update some parts inside IRAM itself. So the first thing that we do is inject a pointer into IRAM itself, into this handler, which also resides in IRAM. So now another location which we injected is now part of this handler list, of the secondary handler list. And what we also do is inject a payload of shellcode, basically, which we put into IRAM as well. And then as a second step, we can use the OX1C handler again, use this flexible function calling mechanism to actually specify our previously overwritten index. And you need to pass not only the function point, and you have to do some metadata around it for it to work at the end, but basically you inject your own handler there, and then you can jump to your own shellcode. And let's see what this does in a chain. So we do the first one, the OX80, write the payload as well as a reference to it, and then we call it, and then saying it in Ali's words, with this technology we are going to rocket the PLC. Some word about this stager payload first. So it's, as I indicated before, it's a bit of a slow, error-prone, kind of painful way of writing memory. So I had to get those values actually written and not an error to be returned there. You had to do some masking of setting everything to only 1 bits before, and then having not too much. I don't know where it comes from, those errors, but we had to work around some stuff. But it's kind of error prone. So what we did was inject a small little chunk of code in there, which would be able to talk to us again as if we queried this handler. And then this little stub, gives us the opportunity to write to memory in a more flexible way and also in a faster way. And this way we can inject arbitrary payloads. And now that we can inject arbitrary payloads, we may want to play around with those a bit. And this is where we have a little bit of a demo time, and we will show you a video or different videos pieced together about this. Oh, does it go?
So here we are going to test the existence of a special access functionality in the PLC. In the up is basically going to be all the packets which we send and receive from the PLC, and in the down is basically the script which we have in our remote machine, which is connected to a PLC and we execute. And if the PLC does have this special access functionality via UART, it's going to respond to our packet. And as you can see here, the PLC responds, and we are also actually installing a custom hook within the PLC, and also get the response, basically MFGT1 and CPU.
This was the first demo of it?
In this demo, we are going to dump from the RAM of the PLC, from the Siemens S7 PLC, using this special access feature. So for doing that, first, actually, we are going to connect to our infrastructure. So basically, we have a server which is connected to a PLC. It's a remote machine. We also create a SSH tunnel. So we are doing a port forwarding of all the requests to our local machine, basically here. As you can see here, we create our tunnel. And then after that, we are going to basically dump the content of the memory of the PLC. So here we show that the PLC is actually live, so make sure that everything is working. So this is our port forwarding feature. So basically we are connecting to port 5555. And as we can see, PLC is alive and our tunnel is working. And basically we also, for a test and see that it's actually is not a static test, we are also going to log in to the PLC. And yeah, so as we can see, if it loads, the PLC is working basically, so it's in a run mode. And so next what we are going to do is that we are going to get the actual firmware from the Siemens website. We already downloaded previously, this UPD files, and then we save it in a folder called out as FWBin. So it's basically decompressing LZP3 compression, which Siemens uses. And basically now we have the actual firmware, not the compressed firmware from the Siemens website. Next is actually we are going to compare this firmware with the one which is residing in the RAM of the PLC, just to make sure that the data which we are dumping using the special access feature is correct or not. So first we are loading into the binary, and I don't want, because it takes so much time, we are going to basically just compare with a small part of the binary. So first we have to rebase the program, because the starting point of the firmware will be different, because the starting point actually in the PLC is first bootloader and then the firmware. So now we rebase the program, and you can see that IDA automatically also find all of the functions. And here's an example function within the firmware. Basically, it's a part of parsing some GET requests in the HTTP in the 691E28 address. And basically what we are going to do is that we are going to, for example, dump 256 kilobytes of this binary and export it from the actual firmware of the Siemens to a file, which we call it FW0x691E28, so for 256 bytes. Next is that we are going to dump the content of the memory from the same address, basically as I'm writing here. We are going to dump the content of the memory from basically the content of the RAM from the PLC, and then next is that we are going to compare it with the firmware which we downloaded and unpacked from the Siemens website. Only a few bytes, because we just want to check the content. Also, we are intentionally slow down the speed of the dumping the content from the basically PLC using UART, because we want to make sure that the contents of the dump is actually valid. So that's it. The content is dumped. So mem dump 00691E28, and we are going to copy it back from our server to our local machine here, as you can see here. So we are going to SCP, and yeah, that's all. So now we have the SU file. So FW is the actual firmware, the static firmware downloaded from the Siemens website, and FW, the mem dump, is basically the version which we dump from the RAM of the PLC. And we are going to compare them, and we are actually, as you can see here, all of the binaries are matching. So there is nothing different between the binaries, these two binaries. So basically it's exactly matching as expected.
All right, so this way we could get Ali here just a bit. Oh, was that? Okay. Okay, yeah. This. I'm not sure if all parts of the video are shown, but we have like a part here. Yeah, I think we can see the most important part. So what we do now is having a little demo about that we can actually have back and forth communication between the two parties, the PLC, and then us as a connected device. It was from a laptop, and here we can see that the Siemens PLC is sending us greetings over and over again, and we actually receive those. See that it actually works for some seconds, but. And now, the most important thing, of course, about the PLC, what it has to be able to do, we thought, was playing a game. And here, if somebody is not familiar, Ali is playing this game masterfully to a draw, which it should always come down to. But we thought the Siemens PLC also has to have some gaming console qualities. And this is what we did here. And now Ali is going to inject those another payload that we wrote into the PLC memory. And first of all, we see the handshake, and now we are uploading our payload. From here, it starts uploading the payload, shows percentages. Now we can see that the PLC actually gives us the chance to play some tic-tac-toe on the device. And here we can see player 1 indeed won, got a 3 in a row, and this is where we could boot to the normal firmware operation. And this is where this demo ends. All right. Okay, what does this all amount to? What did we see? First of all, we see that programmable logic controllers are becoming more and more complex. We identified different components which are from a complexity perspective, maybe get interesting attacking targets for a potential attacker, or at least we have to make sure that those components which are kind of complex are not prone to being attacked too much. And we have to make sure that they're actually secure. We also saw that Siemens is one of the vendors who, in our experience, is kind of at the front of what is currently being done in PLCs. The game is being upped, and some hardware features are used to protect memory. There is some restrictions on what, for example, the MWSL language can do. So recently they changed it the way that no file writes are supported anymore by MWSL in order to decrease the attack surface a bit. And we saw changes to bootloader chips which are no longer writable. And so different things happen there which are making it harder to intrude such a system. So we saw also this kind of legacy functionality, which we can only guess why it's there. It has a lot of diagnostics functionality, so it's good for developers probably to do some diagnostics even when the firmware doesn't boot itself. But we should also push the vendors to maybe remove those features, because if, for example, in a supply chain we had this kind of device go in the wrong hands could use a feature like this and update firmware on the go. And then it's hard to ensure that the same state which it was sent in from the factory is actually the same state that it is in when coming to the customer. At the same time, removing those kinds of features also removes the opportunity for researchers such as us to have introspection into those systems. So they're actually kind of interesting for us to work with, and they give us more insight and introspection into those systems. So vendors maybe at the same time want to think about opening up their systems in some way to the scrutiny of researchers who have good intentions in a lot of cases, but who are not able to get any access. And so the right people may not get access and the opportunity to, or even incentive to look into those systems. And maybe those people who we don't really want to get access to it with a lot of resources, they can more easily get that in the end than the researchers that we actually want the work to be done by. And also we saw that there are a lot of bits and pieces of a PLC that have a lot of complexity, which we also want to make as safe as possible. So there are a lot of things to be done in the future. Finally, we want to thank different people. I think you know who you are and what you did for us. And with that, I'm leaving you with a thank you for attending this talk. And I think we have like 5 minutes left. There are questions, we can take those, like a couple or so. There's also a microphone going around, so maybe if you keep raising your hand, you could. Yeah, over there in the middle.
Hi, first, thank you for your presentation. So I'm working for Schneider Electric, so thank you for helping us to improve our PLC. My question is very simple. How many times does it take to you to do all this reverse engineering, and how many people were you to do this?
I actually did the reverse engineering myself. How much time it takes, I did it as a research work for when Ali was a PhD student back then. And I spent part of next to my studies sometime, but it would take some time. I couldn't really put on how many days or so, but if you specifically looked at the bootloader code and then had this intuition, which is also a bit of luck involved maybe, but only looking at the bootloader, finding this, you could probably do in a week, I would say, to get that. Something like this. It's hard to put on actual item. Yeah, and of course you would have to have the basic skills of doing the reverse engineering in the first place. So this takes a lot of time before, obviously, yeah. But afterwards, if you have somebody, I think that would be an estimation maybe. But it's hard to set in stone. Okay, maybe one more question. Yeah, over there.
Yeah, thank you for the talk. I just wanted to ask if you tried to contact Siemens with it and if they responded in any way.
Yeah, we actually had a responsible disclosure like some months ago. So Siemens is aware of this, and they also are working on a fix of how to tackle this. Yes. And the last question.
Yeah, so I know that some Siemens people in here, and the question is a little bit provocative. So, like, as an offensive person who always think what I would do with such things. So obviously, this special feature access, which is obviously backdoor, that is something not what is remotely exploitable. So it's not something what Siemens could claim that they left it there for remote, troubleshooting and whatnot. So you basically have to be physically in front of the device to exploit it, and it's so hard. Very well hidden, so the average person will never find it. So obviously it makes me an impression that it was left intentionally there for people with a specific knowledge that it is there. They can intercept, for example, shipment of PLCs in transit and then introduce something interesting into the firmware of those of the PLCs for the customers who will get them. So when you ask Siemens, what is the purpose of that backdoor or special access feature in there, what was their response?
I think there was just a neutral response, not anything specific about the intention of this. I could see a lot of potential just normal applications just because it's useful. I mean, you could speculate that it's not the best intention, but that's always something you could speculate. But I could see a lot of reasoning for it just being a very handy feature for troubleshooting for a developer, for example. But it's nevertheless, it kind of gives you both modes, and this is why we probably want to get rid of those kinds of things that in the end could pose a threat to the actual PLC, which is running at the customer's site. Yeah. Okay, I think with this, we're about out of time. Yes, I get the 0 raise, so we're perfect. All right, thank you, everybody. And if